got on your Mac. The principles are the same. So what I want to do today in the talk is to go through some fundamental principles of Unix explained in Perl. So first, an apology. I'm really sorry I did not have time to write my own presentation software, so I'm using the outliner feature of Vim. I initially felt bad about this, then I saw Larry's talk, and he wasn't even using the outliner feature, he was just using Vim. So now I feel perfectly happy. So, as I mentioned, explaining some fundamental Unix concepts with Perl, with a little bit of historical context. History is always important. If we don't, what's the thing about mistakes, learning from history? I don't know, but Unix has lots of different mistakes. It's also about 44-ish years old. So some of these mistakes, you will understand why they were made, because 44 years ago, things were very different from what they are now. But those mistakes have still influenced Unix today, and we have to live with it. So enough of that. We're going to cover two main fundamental concepts in Unix today. And if you are a Unix expert, you can probably give up now because you've seen both of these. We're going to cover processes and files, both very important. Processes are what let you do stuff, and files are things that let you do stuff to them. So let's start with processes. Does everybody know from my simple explanation what a process is? Everybody happy? Okay. I'm assuming, by the way, people have got some kind of Unix machine. Is there anybody in Windows? That's good, because it's not going to make any sense. Okay. Yeah, yes. Was that part streamed? Oh, no. So in Unix, there are lots of different processes running on your system at the minute. If you run PS, you will get a nice list of them. They're all started the same way. They're started with a magic command called fork. Does everybody know what a fork is? In real life? Yes. Yes. Okay, so I'm seeing that, the thing you hold in your hand, that's not the right fork, right? The fork is you're walking down a road, and suddenly it gets really confusing. You can pick left or right. Or sometimes driving around Orlando, you can't pick either, and you think, where did the hell my road go? But the idea is you choose left or right. That's the fork in the road. This is the same concept with processes. You have a process running along through its instructions. It gets the command, says fork, and all of a sudden, it splits off in two different directions. It's quite a simple idea. These two directions are two separate execution paths. So now that you've created two separate processes that are just like the old one, you have a new process and the original. The process that creates the child, well, the parent creates the child. The one that runs fork is the parent. Of the two that return from fork, one is the parent, one is the child. This may be tricky to understand. So I've got some code. There you go, some simple Perl code. Can everybody see that? If you can't, move forward, get glasses, request the slides later. Does anybody know what this will do when I run it? So the answer is yes, some people know what this will do when I run it. Yeah. The follow-up question would be, would someone like to explain what it will do when I run it? For those of you, I know some people are here to try to pick up some Perl as well. The $$ is the current process ID. That should give you a clue. So when I run it, it will not find my path. Hold on, let me just get out of this. Sorry. Can we delete that from the live streaming? No. Okay, so here we go. Let's try that again. Okay, so now we're going to run it with the magic key that you now work now. Okay. So you can see we had one start and we had two dones. Did everybody get that? We have start, done, but the fork now splits off in two separate directions. One start, two dones. quite simple. This wait command at the end will eventually, if you wait, get and explain what that's for. So the concept of fork is very simple. The thing is, you don't always want, usually you don't ever want your parent and your child to do exactly the same thing. So you don't really want two dones printed out, you want them to do different things. And the process is also, as well as having, by design, different things to do, there are different things they should do because of their responsibilities. So this wait command that you saw, that's the parent's responsibility. What a good parent needs to do is wait for the child to finish. The command has a sensible name. You're waiting for the child to finish. Some parent processes are not that responsible, so sometimes the parent will quit before the child finishes. In that case, thankfully, one of the other processes in the system happens to be process number 1, who is the great-great-great-great-great-great-grandfather of all of the processes. He will adopt the child. That means he will take responsibility for cleaning up after, since the parent has ditched the responsibility. The other thing that can happen is the child can finish before the parent is ready for it. So the parent may be off doing something else. The child finishes really quickly. The parent's not waiting for it, so the child's kind of stuck there. And this is where the analogy deviates strongly from real life. In that case, the child becomes a zombie. Okay. Exactly. So thankfully, again, as it's not only different from real life, and that doesn't really happen to your kids if you don't wait for them, but also real life zombies tend to be vicious, nasty little creatures that are after brains or something similar. Zombies yeah, maybe the same thing. Zombie processes are just children who are looking for someone to clean up after them. They don't have any brains of their own. What actually happens underneath is everything that was part of the process is, disemboweled and removed from its head, and it leaves just one single little piece of information, which we'll come to later. It's the exit code. So when a child exits, it leaves just this empty shell of an exit code. That's how the child can inform the parent of its success or failure. Because once we've done the fork, we're two separate processes. Those processes, as they're separate, they don't share any information. There needs to be a way, in most cases, for the child to tell the parent whether it was successful at doing the job that was assigned to it. Like, go clean this chimney out in 200 years ago, England. Child goes up chimney, comes back, says, parent, clean chimney, and the parent is happy. The exit code is, sorry, let me go back and finish the wait stuff. I should have shown you this. This is a more responsible looking parent. I'm moving too quickly. Here we're forking. Fork can return, we're expecting it to return this process ID. If it's not defined, then fork failed. This can happen. It's an operating system. Things can go wrong. Usually they don't, but they do sometimes. You have to be able to track when things go wrong. The best thing to do when something like fork fails is just abandon your whole process, because it's probably something you can't fix, and it's probably something you're not going to be able to properly diagnose from inside your Perl script, so just give up and hope it doesn't happen. Then the normal situations is PID will come back. It's either going to be 0 or not 0. That's a property shared by all numbers. They're either 0 or not 0. So if it's 0, that means the path that you've taken is the path of the child. If it's non-zero, it means the path that you've taken is the path of the parent, and this is how you can make them do different things. On the child path, we don't do anything. We just say, hey, child is done. On the parent path, we say, yep, parent is done, waiting for the child, and then we call wait. So that's wait. Now we go on to exit. Code's a bit more complicated here. I'll probably have, yeah, it's all on screen, good. So again, same as before, we start, we fork, we check the fork succeeds. The child prints its little message and then calls exit. Exit 0 is saying, hey, everything worked. So if you've, the standard convention, although in Perl subroutines, we use non-zero for success and 0 for failure or false quite often. In the Unix world, 0 is usually the exit code for success, and anything that's not 0 is usually the exit code for failure of some kind. So in this case, the child is saying, yep, I'm okay, no problems. Then you'll notice I took out the other else here because we don't need it. We're calling an exit. Nothing's getting passed here. Now we know we're definitely in the parent. The parent is doing the same thing. It's waiting for the child. But now when the child is finished, it wants to know what happened to the child. So this exit code that gets returned is returned in the $? variable. You'll see this in lots of other places in Perl because lots of parts of Perl end up doing this behind the scenes, forking and doing something else, then coming back with this exit code. The exit code is a number, and it's split into 2 parts. It's a 16-bit number. The low 7 bits will tell you whether the child was killed outside its own control. We'll get to that later. The top 8 bits will be the exit code returned from the child. And for the observant, you'll notice there's a bit in the middle that I haven't mentioned. I'm not going to. There will be time for questions. If anybody really wants to know, they can interrupt and ask questions. So what we've done here, rather than having to look at a 16-bit output pattern, I have a little function called explain exit that will be occurring in most of my other examples that simply goes through to work out what has happened to my child. So it goes through and said, okay, if the lower 7 bits have something in them, then I've been killed. If they don't say that, so if the lower 7 bits are 0, then the upper 8 bits contain the exit code. So if that is non-zero, it's some kind of error. Otherwise, the fall-through case is the exit code was 0, therefore we're all okay. So when we run this, you'll see that we started, the parent is waiting, the child returns, it says my child finished okay. That's not very exciting. So let's change the exit code to 99. And you'll see now the child is erroring out. The child thinks it's done, the parent picks up, my child's finished with an error 99. So you can choose whatever exit code you want. There has been some attempt to standardize these. There is a C header file called sysexits.h where they have a few exit codes that they're trying to encourage people to use and have been trying for many years. I would recommend using those if they fit. If they don't, make up your own. The one thing to be careful of is don't do this. Because as I say, the code returned in $? and everywhere in Unix is a 16-bit code. The exit code is 8 bits. 256 is 0. So be careful with that. Also, negative numbers, no, we don't have those. It's 8 bits. So stick to numbers between 0 and 255. Does that make sense? Please interrupt me if you want. Or we can move on to the next topic, which would be sleep. If you've nothing better to do as a person, a good option is to sleep. It saves your energy, it helps your body recover. Processes do the same kind of thing. If they've nothing better to do, they have a couple of options. They could spin endlessly in a loop like this, and all that will do is build up lots and lots and lots of heat, and it's not good for the data center. Instead, what we recommend is sleeping. And what will happen there is the process will basically, when it says it wants to sleep, the operating system is like, that's fine, I'll move you over here to the nice comfortable area and let somebody else do something else instead. I'll give you an example of that. Again, at the bottom, you'll see my explain exit function, which I'm not going to talk about again. The top is very similar. The only difference is you will see we've added a sleep 2 in there. That is telling the operating system, hey, I would like to sleep for 2 seconds or about 2 seconds. It's not guaranteed to be accurate. It's usually guaranteed to be at least 2 seconds. It could be much longer. The reason I'm putting this in here is it's much easier to demo multi-process things if you have them finishing at different times. When we have processes doing nothing but printing a message to stand it out, it happens so fast it's not very interesting. So here you can see there's a delay while the parent is waiting, then the child comes back. And again, delay, child comes back. Not very interesting, but during that time the child was having a nap, yeah, we're fine. I don't think we need to talk more about sleep. So far the words have kind of made sense. Another thing you can do to your children is kill them. Yes. In fact, killing, you can kill lots of things. Yeah. Well, we're getting to that. So kill is one of these. I wouldn't call it a mistake. I would say it's possibly one of the features that's badly named. We have many of those in Unix. The problem with kill, the reason it has its name is the original intention was to make the process exit against its will. So the process is doing something you don't want it to do, you kill it, make it exit. The actual implementation of that is what's called a signal. When you run kill, the operating system delivers a signal to a process. A signal is a bit of information that's out of band. It's not coming in from its standard input or other input streams. It's something that will interrupt whatever the process is doing and make it do something else. So kill, again, very similar example. You can see now, it's like the sleep example. We have sleep in, but now the parent is not going to wait for this child. If the child falls asleep, the parent's going to kill it. So the syntax of kill is it takes a number and then a list of processes. That's not the whole truth. We'll get there later. The number is the signal number that we're sending it. And does anybody know what signal number 3 is? We'll get to those later. So we'll maybe not get to that later. Yeah, it's good. So when we run this, previously we saw a 2-second delay. Now when we run this, we'll see something different. We'll see a 0-second delay. And this time, when we explain the exit, it will show that the child was killed by a number 3. So what has happened there? Operating system sent this interrupting signal, interrupted the sleep that was happening, because we know it was during the sleep, and the child then had to respond. The child didn't know what to do with this signal, so it died. The child has options to deal with some signals. We'll cover that later if I speak faster. Okay, now, so far all of my main topics have been system calls. There is no system call called multiple processes, but it's to give an example that one fork is usually not enough. You would then have a maximum of 2 processes running, and that's not enough to do much. So quite often you'll need to spawn lots and lots of children and get them to do lots and lots of different things. There's many different patterns for doing this, but they're all the same. You make lots of fork calls, and then you have to clean up your children. So this is just an example of what we did. And since I've been to Disneyland, I figured I would use the 7 dwarfs. So what we're planning to do here is we're planning in this process to create 7 children, have them do something completely uninteresting, which will be sleep for some random time between, well, less than 10 seconds, and then finish. So if you're doing lots of things across a list, in our nice little for loop, we're telling here that we're going to create a process. We're running the fork, checking the fork fields. Now, if the fork resulted in a child process, we're doing what we want the dwarves to do. So they're sleeping, and then eventually they exit. Now that we've got the exit, we know nothing's getting passed here, so anything out of here is the parent. We've still got one parent process, and the parent is going to record the mapping between the process ID and the name of the dwarf. We're going to need that for later because we want to clean up correctly. That makes sense? It's all, the Perl in this talk should not be complicated. If it is, scream at me. So now that we have all of the children recorded in the kid hash, what we're going to do is go through this kid hash and wait for children. So we know we've forked 7 children off, so we're expecting 7 to be back. Whatever number we fork off, we know that's going to be the number of keys in the hash. So while we have keys in the hash, we wait. Wait will return the PID of the process, the child process that exits. The error code will be in $?. So then we just do some more error checking. If wait returns -1, we have a problem. What happened there is we still have keys in our hash. We are expecting 7 children to return to us. Wait said -1. That means there's no more children. Something very strange is happening because really it shouldn't have returned at all. We don't know what's going on, so let's die. We get to this point. We're assuming success. We have waited on a child. Now, let's see if it's one of the children we're expecting. So we search for the PID in the hash, get it and remove it, and stick its value into D. So if we found a value in the hash, that is, it's one of our children, that's fine, we can continue. But if it's not, if some other process has returned its exit code to us, again, something strange is happening, but it's not strange enough to warrant giving up on everything. We don't know what's going on, but we don't really care. It wasn't one of our children, not our responsibility, so just warn about it and ditch it. Otherwise, everything works. We can say our process has returned successfully. So when this runs, we'll now have to wait for the dwarves to do their thing. So one of the things I want to point out about this is you'll notice that the order in which we created the dwarves is not the same order in which they exited. So that is a very common thing. In fact, should always be expected when you're using more than one process. It's not sequential. It's non-deterministic order. You don't know when things are going to be done. So, final thing I want to talk about in processes is what's called exec. So we're all here at a Perl conference. We all like using Perl, but sometimes Perl may not be enough. You may want to run a program that someone else has written in some other language. So for that, we use a command called exec. So what exec does is takes the current process and completely replaces it with something on disk. So it takes another program from disk, moves it into memory, and blows away your current process and lets the other one take over. So it's replacing what's currently running with something else. So I've been trying to do this for years, replace Perl 5 with Perl 6. If I run this, unfortunately, that doesn't work yet. But what it tried to do was replace the process, and it failed. So you have to, again, handle the error condition. You'll note that there's no if statement, there's no return code. Exec will either run something else, or if it returns at all, it's failed. Because you're not supposed to be there. Its job is to replace your process, so returning is failure. So no conditions, you just die. We could make it work by doing what lots of sysadmins have done instead. Yeah, that works. Okay. So, any questions about processes? Again, I shouldn't have streamed that, sure shouldn't. No. Okay. Now, files. Does everybody know what a file is?
I have no idea.
Okay. Yes! Well, yeah, sometimes we lose the real world analogy. So one of the things that Unix was kind of famous for at the start is this concept that everything is a file. For people who are familiar with Unix now, this may seem old hat, and you may try to think, how could something not be a file? You know, if you've got the whole Unix mentality. But at the start, when they said everything was a file, it wasn't really everything. It was just some things that in other operating systems were not files. So the obvious ones that were shared by most OSs was, normal files with content in them, like text files or some other kind of formatted file. So two common examples of files would be my to-do list or the etc password file. Where Unix was revolutionary is they also created a directory called dev, and inside dev they put other things that looked like files but weren't. So like SDA3 and urandom and other things you find in dev. They're not real files, but they look like files. They have file names. You can do file things to them, some file things to them. Other operating systems didn't do that. This made Unix special. Unfortunately, it wasn't as special as it thought it was. 44 years ago, these were really the only kind of things you had. You had devices like disks, devices like serial ports, make those into files, and you had real files. When other concepts came along, Unix deviated from its own philosophy and decided to make them things that weren't quite files. So they didn't look quite as file-like. You can still do reads and writes on them like files, but you can't look at them in the file system in the same way. If you really want an operating system that does treat everything like a file, the Unix guys got together and created an operating system called Plan 9, which does make everything a file, and extended the Unix concept to cover everything else. So that was the historical segue. So one of the things you'll want to do with files is open them. Open is very useful. I'm sure everyone has seen at least part of the extensive documentation for Open. I'm not going to try to cover it all here. We're going to cover just the modes of Perl's Open that match up with the modes of the underlying Unix Open. With a lot of the other commands we saw in the processes section, the Perl commands were quite closely matched to their equivalent underlying Unix commands. Open is different. Open has, in Perl, does many, many more things than it does underneath in Unix. But the 5 things that it does that Unix does underneath, you can open your files in read mode. Simple enough. You can open them in truncate and write mode. So that means if the file exists, it will blow away all the contents and start writing from the start. You may not want to blow away your contents, so you can do append write mode, which is start writing from the end of the file. Sometimes you'll want to read and write at the same time. And again, you may want to blow away the contents first. So there's 5 basic things you can do with Open. I'm not going to show you any code for those. Not by itself. So the next thing I want to talk about is stat. So you have a file on disk. You want to get some information about that file. So you can use like the -f, -r, -bst operators in Perl. Underneath, in general, they all look at what's called the stat structure, and you can get the whole thing back by calling the stat command. Stat has 13 fields in it that are listed below, giving you quite a lot of information about files. Not all of this information is useful to modern day programmers, or not as useful as it used to be. So I'll try to go through them. Does anybody know all 13? I didn't. But so the first one is the file system device number. We don't need to care about that in general now. If anybody really wants to know, we might hit it later. The only time I'm going to mention the device number is when I mention the inode number. The inode number has to be unique per device. So the device number and the inode number go together to make a unique identifier for the file. Because the file name is not its actual identifier. That's just its name. That's like a sticky label you stick in the front of the actual file. So the actual file is represented by this thing called an inode, which is probably short for index node. They used to have, on the old file system, a big array of where their files could possibly be, and you would just index into the array. That's what the inode is for. On modern file systems, it's impractical due to size to have an actual array to store these, because it would be very large. But they still have to make up some kind of inode number. It's really problematic for large distributed networking file systems because the internal identifier they use may be much larger than the space allocated for an inode number, and then you can get bizarre behavior because in Unix, you can expect and trust that the inode number is unique per device. That's not true for all file systems on today's systems. And if you encounter strange problems with shared libraries and large file systems, that might be your problem. So again, let's not care too much about those. Mode is interesting. It contains your file types and permissions. When you do ls-l, you'll get rwx, r-x, r-x, things like that. Those are the permissions of the file. File type is also to tell you whether the file is an actual file or a directory or something special or some of the other things we'll talk about later. Nlink is the number of hard links to the file. So as I say, the file name is just like a sticker that goes on top of the file to give its name, like this. Okay. So Abigail, can I borrow your badge? Okay. Dave, can I borrow yours too? Okay. So I'm a file, and when I start, I have one name. My name is Marty. But you know, I have two names. Okay. I'm Dave and Marty. And this is actually legitimate because one of my middle names is David. Well, this is completely not legitimate because one of my middle names is not Abigail, but now I have three names. Notice there's still only one of me. So I'm the file. My unique identifier is actually my device and inode number. These are just badges. But what we have to do is we need to track the number of badges that a file is wearing. And we do that with this nlink field. So every time I put a badge on, nlink increases. And again, thankfully, where this deviates from the real life is every time I take a badge off, yes, the link count decreases. But if I were a file and I did this, as soon as I stopped talking, I would disappear. Maybe you're wishing that happened now. But again, the important thing is, that's why I don't stop talking. The important thing is, it's reference counting garbage collection, but it only happens when the files have no links and they stop being used, when people stop reading from them, when people stop listening. So in this case, you'd all have to cover your ears. I would disappear. Sometimes on your file system, you may find that your file system is full, but when you look at all the files, they don't add up to the right amount of space. That could be because someone has tried to delete a file, which simply means taking its badge off. But if the file is still open, it's still on your disk, it's still taking up space. You need to find out what has it open. When you kill the thing that has it open, the file will disappear, you get your space back. Did that make sense? I'm still here. It must. People are still listening. Then we have UID and GID, user and group. Am I running out of time? No? Okay. Cool. That's who owns the file and what group owns the file. We're not going to talk about permissions too much. But then we have this interesting field called rdev, which is the device number if this file is a device. What that is for, remember I mentioned the special files like /dev/sd, I'll go up here, SDA3. What this is for is that exists as a name on disk, but instead of having actual file contents, the rdev field is populated and gives its device number, and that's how you can turn an actual device into a file and then mount it as a file system. This rdev thing doesn't matter for normal files, so we're going to ignore it. But it would be the same as if you mounted this file system, anything on that file system would have an entry dev, which is the same as this thing's rdev. That doesn't make any sense. Let's ignore that. So now we get on to some of the interesting ones. I'm going to skip size temporarily because everyone should know what size is, I'm hoping. Now, A time, M time, and C time. These are 3 times. Does anybody know what they're for? What was the last one? Yeah. Confused time. Yeah. So there's a couple of problems with these. Again, one of the greatest mistakes they made in Unix is this A-time field. It's the time the file was last accessed. So one of the Linux kernel guys said that every file system performance improvement made over the last 20 years still hasn't got anywhere close to the improvement we'd have if we just switched off A-time. So if you want to make your file system faster, forget about tuning it, switch off A-time. Things may break, but it's a really silly idea. Basically, every time you look at the disk, any part of the disk, directories, files, like any part of the directories, it has to update the disk and say, oh, this was accessed, oh, this was accessed, oh, this was accessed. So every time you look at the disk, you're doing lots and lots and lots of extra writes. That's a huge performance killer. So people do turn it off or partially disable it in strange ways, so please do not trust this field. M time, that's the sensible one. When someone actually changes the file, this is the time the file was changed. That's the most common one. Use that. The C time, lots of people, it is, as was correctly pointed out, the change time. When this stat information changes, C time is updated. Originally, it actually was the creation time. And even though it's 44 years on, lots of people still think it's creation time. And quite often it matches. Some people will create a file and never change the properties at all. So it can be the same as creation time, but again, don't trust it as that. It's the last time the properties were changed. So what I want to do now is do size, skip block size. Block size is for performance, we don't care. And blocks. Okay, so the last field, number 12, is the number of 512 byte blocks that are allocated on disk for this file. And number 7 is the size of the file in bytes. So the important thing to know here is these things may not match up. Okay, so I'm going to give 2 quick demos. First, general stat, then I'm going to explain why block size and file size doesn't match up. This is a really simple program that just uses the file stat module so that I don't have to remember what the field numbers are to print out information about the fields. Most of them are numbers. One of them is a number in octal, so I want the formatter for that. 3 of them are times, and the rest of them are just numbers. So let's stat itself. That's the kind of information you'll get back about the file. Not very interesting. Now you know my user ID. What a shame. Notice at the bottom, block size is 496. That's nothing to do with the blocks underneath it, which are measured in 512 byte blocks. Okay? So even though they look similar, they look related because one of them is block size, one of them is blocks, they're not connected. It's confusing. So ignore block size. That's a recommendation for if you want to write in 4096 byte chunks. So you'll see the size is 405 bytes and the number of blocks it takes up is 8. So 8 512 byte blocks is quite a bit bigger than 405 bytes. So why isn't it just one block? Well, we don't care why it's not one block. The important thing is it doesn't match. So the reason it doesn't match is we have these things called sparse files. Or that's not the reason it doesn't match. It's one of the side effects of the fact that it doesn't match. We have sparse files. Has everyone seen a sparse file before? Okay. So what we have here is a little program to simply print out the size of a file and the size it takes up on disk by multiplying the number of blocks by 512. So they won't match, but we're hoping they're kind of going up roughly in step. So we start off creating a file, do horrible autoflush. So we show the size of an empty file. We're going to add 12 bytes to it, show its size again. We're going to add 4085 bytes to it and show its size again. Then we're going to add 1 terabyte to it. By cheating, we're going to seek 1 terabyte towards the end of the file, and then we're going to write some text. So the problem we have now, we can see at the end we have this thing, this huge 1 terabyte file that takes up only actually 12K. That's 3 physical blocks on disk. You'll see the discrepancy there between the file sizes. A 12-byte file takes up, takes up 4K on the disk. So creating lots of small files on the disk will eat up your disk space much faster than you may expect. Small files are not good for your disk. Again, it's for efficiency reasons. The original reason we had 512 byte blocks, that was the smallest write size to the disk. On my file system, the smallest write size, sensible write size, is 4K. So every time you write anything at all to the disk, it's going to need an extra 4K block. Does that make sense? The thing you need to be careful about with these sparse files, if you look at this file on disk, this 1 terabyte file, with LS, it'll say it's 1 terabyte in size. If you try to copy it somewhere else, it will actually, even though it's only taking up 12K on disk, if you try to copy it somewhere, it will copy 1 terabyte of data. If you send it across the network, it will send 1 terabyte of data. It will compress very well because most of that data is 0. But if you don't compress it, and even if you do compress it, it will take a long time because it will have to read 1 terabyte or think it's reading 1 terabyte before it compresses it. So it's cheating at the file system level. The other very important thing is it doesn't work on all file systems. On all Unix file systems, they have to expect this because people use this. If you're running, say, a Windows file system from your Unix machine, do not do this. It will write a 1 terabyte file, which is a big problem because I have a 128 gig disk, so it's not going to work here. But sparse files do not work on all file systems. We can explain later how they work if anybody's interested. Okay. Let me go through this really quickly since we have 10 minutes left. Opendir opens directories. Unix philosophy, everything is a file. Back in the old days, a directory was a file. You would open it, you would read through it, look for particular patterns, and it would give you a mapping between a name and an IDO number. But nowadays, with modern file systems, and even before they got to be that modern, it became inefficient to store directories as normal files. So directories are now no longer normal files. You can't sensibly call open on them. You have to call opendir. Opendir always existed. It was a way, it was a wrapper around the library call. Underneath it used open. It doesn't anymore. It uses other features to read directories in a file system specific way. You can only read via opendir. Link, that we saw before, is the thing that creates these links, puts the badges on. Unlink takes the badges off. And rename is effectively an atomic way of doing unlink, another link, and unlink again. So it removes the old file, it links, removes a new, it's bizarre the way it works. It removes the target file, which I've called new, it links the old file to the target file and removes the old one. The advantage of rename is there's no race condition. If you did this with unlinks and links, there would be a time, maybe a very small time, where the file called $new would not exist. With rename, that doesn't happen. Rename guarantees that $new will always exist. The reason we call links hard links, at the start there were only links. One of the disadvantages with a link or a hard link is it must be on the same device. It could not span file systems. So to work around that, we have these things called symbolic links. A symbolic link is like a symbolic reference in Perl. It's simply a name that you then get reinterpreted by the operating system. It's just a path name. The important thing to remember about symbolic links is the target may be bogus. I mean, it may not exist. Right? It may not even look anything at all like a file name. So if we try to give you an example of that, I have created 3 symlinks. You'll see the first one points to a file. It kind of works. The second one looks like a file name but doesn't exist. And the third one doesn't really look like a file name at all. Because inside this was that a hint? So inside the symbolic link, I'll show you the code again. We're using, instead of stat, we're using lstat because we want the information about the link itself. Then further on down, we're statting the same thing with stat, not lstat. And stat automatically follows, like all file system operations, it will automatically follow the link. We're not dying here because we know half the time it's not going to work. Thank you. And run it again. You can see the differences up here. The symlink size matches the size of the file name it's supposed to be pointing to, or the random bit of text that we've inserted instead of the file name. So you could use symbolic links to store little short notes. They store themselves more efficiently than files do on lots of file systems. But in other cases, they still take up 4 blocks or 4K. In 5 minutes left, I'm going to close this, and I have a last section. We're not going to get all covered in 5 minutes, but we're going to start. This is not a typo. Everybody's heard of daemons in Unix. They are processes that run in the background and perform certain functions. They're like child processes, but there are things you need to be careful of. You don't want your daemon accidentally getting a signal. So, two other modes for open. We can use this ampersand thing. That does what's called a dup or a dupe. It's short for duplicate. It effectively copies the underlying file handle. And we have some special files that are device files that I want you to know about, dev null and dev zero. Dev null is a universal, they're both universal syncs. That means you can write to them as much as you want. They will just throw away your data. I'm sure everybody knows about those. They're both sources as well, but their sources are different. If you read from dev null, it immediately ends the file and gives you nothing. Dev zero will give you a continuous stream of null bytes. We're not getting through all the signals. I'm going to overrun for 5 minutes. Does anybody care? Signals, as we mentioned before, are sent with kill. Usually they will cause your death if you don't listen to them. But we have a bunch of different signals. Some of them do not do that. I've listed some of the signals I like, some of my favorite signals here. I'll try to go through them quickly. First, here's a demo. What I want to do here is catch a signal. So here I've set up a signal handler that's catching a sig called int. So when I run it, it's going to go through this loop. I don't want it to do this. So I'm normally, with an annoying program, I'm going to hit Control-C to stop it. I hit Control-C. Okay. So there we had programmed. We've programmed to catch the signal and eventually quit if you're persistent. That makes sense. There is a quit signal, which does something similar when you hit the quit key, except it'll cause your process to dump core. So 2 behaviors we've now seen. You can catch the signal, you can die. 3 behaviors, you can dump core and die. Hop, does anybody know what hop is? What does that mean? It does exactly mean disconnecting modem. Remember, Unix is 44 years old. That's older than the internet. When Unix was created, sometime after it was created, when they eventually added communication, they only had telephones. Hang up means please hang up your phone. It will usually cause your process to terminate because someone's just hung up on them. You can't do that on me. You're trying. I know you are. Terminate is terminate with a polite death. You have a chance to catch the signal. Kill is one you can't catch. If I send your process a kill signal, you'll never know, you just die. Stop and continue, well, they stop but don't exit, so you'll be frozen in time. Continue is unfreeze yourself. Child is, hey, your children are finished, you should do something about it. It will, winch is your terminal window has changed size. Obviously, that will not kill your process by default, otherwise windowing systems in Unix would be very, very painful. Alarm is your alarm clock in the morning. It will kill you, but then it's your own fault because you asked for it. You typically schedule an alarm, say, wake me up in 5 minutes. Quite often, that's how sleep is actually implemented. Sleep is schedule an alarm for 2 seconds later and do nothing. Segv, everybody seen the segmentation fault? This is a topic of a whole other talk, and there's no time to do that now. FPE is a floating point exception. Be careful with real numbers because they're dangerous. If you do things with real numbers that you shouldn't be doing with real numbers, your processor at a very low level will go, I have no idea what I'm doing, and the only way, it can't give you a return code because you're expecting a number back. If there's no valid answer, it has to give you an exception. Be careful with this. Usually somebody else catches it and does something sensible. Pipe is an interesting one. This is run when the other end of your pipe is closed. And some examples. From a shell, you're catting a file into WC. Hopefully everyone knows what cat and WC do. So WC counts stuff. It will stop when the input ends. That's a well-behaved pipeline. Everybody's happy. Problem is dev0 is an infinite stream. So what will happen if I cat dev0 to WC? Well, it's an infinite loop. It'll never stop. So don't do that at home. What happens if I cat dev0 into head minus C32? Well, it will stop. Head will read 32 bytes, then it will stop. Problem is, how does cat stop? Yes. So what happens? Cat gets a signal to tell it that cat's going around the loop going right. It's not checking for anything else. So when the other guy disappears, in this case head disappears, cat gets a signal, SIGPipe will kill it. I like this demo. I don't know why I like this demo. I've created a little pipeline. It looks much uglier in Perl than it does in Shell. But here we go. We have the left-hand side is just going to go around, say, ping in a loop. The right-hand side is going to read in one line and then stop. And here's the pipeline function that I've done to implement that. It's a bit long. I'm not going to explain it. So there we go. This time the guy caught a SIGPipe and exited stopped cleanly. So we can see here where I've done that. We have SIGPipe is captured and we've exited cleanly. I'm going to stop there. If anyone is interested, I have one other bit of code. Which goes through the process of demonization, but it's a bit long and I don't have any time. Thank you very much for listening.